So a couple of small corrections. Number one, I'm no longer chair, even though the professor and chair. Let's just say professor and happy to be former chair. It's a better introduction to what I'm. But a little bit of background. So Demos and I were graduate students together. I am 65. He is not. He is not. Let's start with the obvious. But we were in the former electronic systems lab, currently LIDS. So indeed, we were graduate students in a place where control was very similar to servo mechanisms. We looked at physical systems primarily. Aerospace was big in those days. The F8 adaptive control, the F8 was one of my first projects. But we were evolving from the control of the classical control of servo mechanisms to control of broad systems at a much broader scale. And many of us who were educated in that time period were kind of infected by that idea. We were looking at economics, transportation, power systems, military systems, organizational control, manufacturing, communications. I'm struck by, Semyon's presence here. So, I know that he was one of the first to switch into manufacturing control and production systems in that area. Tamer was a student also looking at the game theoretic economic control in those days. Praveen, as he mentioned, was kind enough to stop by MIT for a year in sabbatical and teach us about, basically stochastic control and martingales. Those of us who were lucky to attend his classes. But anyway, what many of these applications had in common were that suddenly you were talking about very large systems. Things not with 4 or 5 states, but many, many states. You were also talking potentially about distributed information. You were talking about systems that had multiple decision agents, perhaps with diverging objectives. And that inspired a lot of attempts at generalizing the fundamental theorems of systems and control to that class of problems. And in doing so, we found that there are plenty of limitations and lots of thesis to be done in those days. And indeed, we found, starting from things that we know about non-nested information, the Witzenhausen counterexample, the lack of decomposition of applicability of dynamic programming, the presence of signaling in distributed control, the types of issues that Jan spoke of in his talk and the like, and even some of the indirect communication and signaling problems like Praveen discussed in his ideas. So we discovered many limitations in those days that kind of led to subsequent work. Typesetting was different in those days. I don't know how many of you read this thesis or you have this document. This is, by the way, the MIT official library copy of this document. And you can see that corrections were done by hand because once the typesetter left it, you had to write the right thing, but you wrote it. You didn't retype it because retyping meant cutting and pasting with scissors and glue. And therefore, sorry, that wasn't work. And also spell checkers were kind of funny. I don't know whether your libraries would have accepted this one. I know that Al Avestruz's thesis probably has MIT spelled correctly. My librarian won't even accept it with the wrong margins of error, so it will never, if you insult the institution by misspelling the names, they'd never let you graduate. Indeed, they delayed his graduation by 4 months, as you can see. Nevertheless, Demos was very interested in the overlap between the theories of communication and distributed control. His PhD thesis topic was very much on the topic of real-time rate distortion problems. Not the classical infinite background communications theory, but what could you do in real time? Indeed, it was focusing on bounds on the performance you could achieve. And of course, as all your former students have read this, but this is just more for the others who have not had to read it. I, by the way, was a reader of Demos' thesis. And this was not because I was an official advisor to Demos in the slightest, but rather because I was working at the time as a postdoc, and one of his readers basically said, "This is very technical, would you please read it?" And as postdocs, yes, yes is the right answer to all such questions. We did read it, and as I was a reader of his thesis. So Demos graduates and joins industry, Alphatech. By the way, that being a reader in his thesis was the first time I actually led Demos into a problem. From then on, the rest of my career, I followed him into problems. So Demos leaves for industry, joins Alphatech. We had a common advisor, Nils Handel. And so his advisor was the founder of AlphaTech. He invited Demos to join. But he continued very much his research on large-scale systems with distributed information. He did some great, for an industry place, this was an interesting place to be, and he did some fundamental work on team problems, games, consensus, you've heard some of it, not the basic consensus that Praveet talked about, not the averaging consensus that you see these days in the literature. Indeed, it was kind of amusing to be in Los Angeles a couple of years ago at the CDC. And at one of the game theory sessions, I'm sitting there, and there is a talk by a student of Jeff Shamma's, actually a postdoc of Jeff Shamma's. And of course, normally, as you know, Demos doesn't travel to many of these conferences for great reasons. But a lot of his students were. Unfortunately, I looked around the audience, and I didn't see any of his students there. And so I said, well, maybe I should say something about this. Because the talk, if I remember correctly, was named, it was sort of a distributed detection problems. And I said, you know, this, I remember somebody used to work on this. And so as I hear the introduction to the talk, I said, let's see, optional stopping with two detectors. I think I've heard that problem before. And indeed, it was the decentralized world problem. Not seeing your students in the audience, Demos, I very quickly downloaded the paper from the website and emailed it to Jeff. So before the end of the session, Jeff, his student, was talking to his students saying that, you know, you should do a deeper literature search next time you work in a problem 30 years after the original publication. And so anyway, this was Demos. So a lot of the work was kind of nice and fundamental. And
it says something about the review process.
It does indeed say that too, Taber. It does, because I mean, it took me approximately 5 lines to realize this is the same problem Demos looked at.
Never more than 10 years in the review process. You discovered exactly.
Exactly. So anyway, this was, you know, what can I say? So I followed Demos to AlphaTech. So I joined him, and we were collaborators at AlphaTech for 4 years, and a lot of our joint work stems from those years. Eventually, he leaves AlphaTech and joins Michigan, and he was it's a precursor to this event. He founded a nice department and has stayed here the rest of his career. It was an example that others followed. I mean, I did so a little bit later. Ahmed Tufik, the chair at the University of Texas, Austin, formerly at Minnesota, also did that, and a few others along the way. But Demos basically continued the same research directions that had puzzled him all through his career, but he added a few things. A very strong component of mentoring and teaching, evidence of which we see all over this room. It's very nice. He also managed to avoid the curse of administration. And I say that with admiration because I've been cursed, and so therefore he managed to stay on the academic track, and it's to his administration. Now, first of all, I apologize to all of you who worry about networks. Rajiv, Manjari, sorry. My job is to destroy them. Or at least to make them work poorly. How's that? The rest of this talk is about how do I make your networks not work. And so, what can I say? I'm a game theory person. Tamer's a game theory person. We like to interfere in games. We don't like this self-supporting, we're all on the same side type of thing. We prefer to be on opposite sides at times, and we like zero-sum games sometimes. So here's the problem I'm going to talk to you about. And for some strange reason, I have some, okay. No, some display things. It so happens. Anyway, I have a network that I can attack. My hope as an attacker is to make the network perform as poorly as possible. However, the network's an intelligent network. Most networks today are adaptive. And if I degrade parts of its operations, they will try to adapt and restore those operations elsewhere. It's even worse than that. I may have backups that I don't know about when I'm attacking. I mean, there may be aspects of the network that I'm not aware of because it's not in use right now. They're reserves. They're reserves that can be brought to bear in the network should the network be degraded. But if I were just observing normal network operations, I'm not even sure of their existence. So this creates an interesting situation of how do I attack something that I only know partially, and it adapts over time. There are many applications of this type of environment. We've seen some today, power systems, distribution networks of that type. Transportation networks, road networks in the tape. Communications. There's some interesting applications in drug smuggling, cybersecurity, network attack in this context, air marshal deployment on airplanes on transportation. There's a lot of other things that carry this along the way, so let me not dwell on those too much. But let me instead tell you a little bit about what's known about this problem. First of all, who worries about this problem? A lot of people in places like the Naval Postgraduate School and Operations Research Departments. It's their job. They worry about enemies in places like that, and so there is a very natural place. So a lot of the early work in this place, if you recognize some of the authors, Kevin Wood is at the Naval Postgraduate School and the like, they dealt with first purely from an operations research perspective. It's a stationary problem. Well, how do you say, well, you design a network to be adaptive. I will degrade it, it will respond. Hopefully I'll try to minimize the effectiveness of the network after what I do. Eventually, they start looking at it as a stackable game. You attack, network reacts. Okay? And then they look at it a little bit as, first they start with perfect information, then they start adding some stochastic elements to it. Suddenly you're not sure the attack's going to succeed or not. That's the aspect of stochastics that come in. Eventually, but fundamentally, most of the work has been focused on a very static view of such a problem. Whereas in reality, it's more of a dynamic way. We worry about dynamic systems. We worry about things that evolve over time. So the questions you can ask is, what happens if you have the opportunity to do this degradation over time? What effects and what interesting behavior can you get? I won't get to that till the second part. But let's start with an application. Here is something where the lines, by the way, let me say that I love industry-generated color diagrams next to beautiful art on both sides of the board. The color schemes have been matched the arts on both sides, the light greens and the other ones. And the other thing about it, I said, we just can't match that. This is just auto-generated graphs generated by Python, and who knows what they look like with small lines. But this is, in principle, a power system distribution network. You had generators, you had some sinks that are occupying most of the power distribution. There are approximately about 400 arcs that you can't see because I can't see them even this close to the board. And there are about 300 and so nodes in this context. You can imagine power flow limitations here. The goal is to maximally disrupt the service of this network. Suppose you could take 5 arcs out. Which ones would you do? Suppose you could take 10 out. Which ones would you take out? These are the kinds of things examples of the problem. So let me give you a bit of the formulation of the problem. And so, well, first of all, once some easy results for the one-stage problem, let's move on to the higher level problem. So you have a budget that tells you how much you can actually degrade a network. How many things could you attack in this context? But, of course, your attacks are not guaranteed to be successful at removing those elements. So there's a probability of success in this context. And you know that if the outcome of the attack happens, the network will try to adapt to that attack and adapt its operations on what survives. So think of a network that fundamentally is trying to deliver flow. It's a max flow network. Has a source node, a sink node, and then based on that, it's going to try to deliver max flow based on who succeed. Well, this is basically a classic max flow from a source to a terminal type of formulation, conservation of flow network in this context, with one little caveat. The flow may be limited by whether an arc is actually physically surviving or not. There's a variable there, an uncertainty variable, a random variable, omega ij in here. So let's notice that I parameterize the flow you can deliver by what success the attack has. Now, what's the attacker's problem in the Stackelberg idea? Well, given that that's the network's response, I want to minimize the flow the network can send. The expected flow the network will be able to send after I attack it in this context. I do have a budget for the attack, which is here. And there are a couple of definitions here. There's some issues in solving this. First of all, that function, you could say, well, sure, it's an integer program, it's hard. Yeah, but relaxations exist. So what's if you relax the variables to linear variables rather than integer variables instead of 0, 1? Well, that function h is concave. You don't like to minimize concave functions, you like to maximize concave functions. So this is the sum of concave functions. That's even no structure to speak of that's desirable, etc. So what do you do with problems like this? First lesson in control theory, never accept a constraint, always make it unobjective. Send the variable that you have to the as a penalty function. So suddenly, the random variable, the random survival event variable is in the objective and not in the constraint. These two provably have the same value in the max flow. The two formulations give exactly the same value. But this is convex. Why convex? It's the maximum of linear functions. Convex functions. Therefore, now you can start relaxing things because now we're going to minimize a convex function, not maximize the convex function. So now you're starting to get some interesting behavior. You also have wonderful probability inequalities, Dubin's inequality, among others, but this is Jensen's inequality in this context that allows you to basically say that you could conceivably, instead of having to minimize over an exponential number of max flow problems, you could minimize over one max flow problem, which is nicer, much nicer. You can actually do that in computation. Of course, it's a lower bound. You can get tighter lower bounds by using finer filtrations of the outcomes, conditional filtrations on the subsets of outcomes, and you get tighter and tighter lower bounds. If you combine this cleverly with an optimization approach and use it in a branch and bound, you come up with an algorithm that's relatively fast and can deal with sufficiently large networks in real time, as I'll show you in a couple of examples afterwards. This is some of the early work that Jeff, my student, and I did. And some of the results we were able to do on that IEEE network with 33 sources, 36 sinks, about 300 nodes, about 400 arcs. Our algorithm is the blue algorithm in a log scale computation. And the horizontal axis is the resource bound. Just how much action can you really take? You can imagine the combinatorics. Combination of 1 out of 400 arcs, that's 400. Combination of 9 out of 400 arcs, that's 10 to the 10th. Sorry, that just got a little bit out of hand. That's why you see a little bit of growth at the end. If you look at what the enumeration cost here would be of how many options you're looking over to get an optimization, we're getting something of this nature. However, these are a couple of the best algorithms that were proposed in the literature till then, and so we're certainly performing well in this idea, but this is a static problem, as I said. Not actually, it turns out if you looked at this one, the hardest one is 10 to the 17th in that order of possible solutions we were dealing with. Let's talk about the multi-stage problem. Dynamics. After all, we're systems people. We like dynamics in this context. What does it look like? So let's consider the case where you can attack over multiple stages. And we have the case I alluded before, where the network has some assets in reserve that are not well known to the attacker. But they will become known if the network uses them. So they can be attacked subsequently. So you can think of, okay, there's this link, this power station that hasn't generated anything because it's a reserve power station. Suddenly gets brought online. Oops, so suddenly you start seeing power flow out of that network. Now that I see it, now that I know it's there, now I may actually figure out how to do about it later, something of that nature. So this creates what I call a dynamic zero-sum stochastic game with imperfect information because the attacker has imperfect information on the network assets. The network has perfect information on what it has, so we have a nested information pattern. That structure is essential, by the way. Without that, we would suffer a lot more than we will later in the talk. We will suffer some, but we won't suffer as much. To illustrate very briefly, suppose I had the simplest network with 2 arcs. But the attacker doesn't know whether the arcs are there or not. So if you look at this, this is basically a probability distribution of the attackers where red and blue are corresponding to red and blue on the, that's as many colors as I can draw. And it's corresponding to red and blue in this context. So you can see that there's a probability in the belief set of the attacker. It says it could be one of these network states, but I'm not sure. Then it can choose actions. And based on the actions it can choose, the network there'll be a random outcome. I took an action. I may succeed or may not. Then the network, depending upon what happens, the network will flow, and there'll be some payouts according to the network to say, I'll be able to do this. This is a one-stage game with uncertainty. This can be solved. This is not hard. More interesting, of course, is when we go to more dynamics. So let's talk about a formulation that looks like that. So we have two players. X will be a maximizer player, Y will be a minimizing player. X will be the uninformed player, Y will be the informed player in this context. X moves, Y moves, then something random happens. There's something. Here's a typical play. You start at a state, action, action, new state transition, action, action, new state transition, something of that fit. What does X know? This is the uninformed player. I only see the actions. I never see the state. What does Y know? I see everything. I see the state. I know what's happening. If you manage to kill my link, fine. I know you did. I know that I attacked it, but I may not know I killed it until you use it. So if I see you using it, I'll learn it. Anyway, this is the abstraction. From then on, there'll be no attacks. There'll be just X's and Y's. Nested information. Notice that what's known to X is known to Y, but what's known to Y is not known to X in this idea. Okay? And we have some prior distribution in the initial state in this structure. So how do you solve these things? Well, okay, you can say, let's face it, it's a discrete state game. Yeah, maybe a large number of discrete states, but it's discrete in the end. It's like chess, deterministic, known. We can solve it. From a game theory perspective, we've never liked chess. Too easy. We like bridge, a lot harder. Uncertain, random. So anyway, there's a finite number of pure strategies. So you could say, let's look at mixed strategies. Let's formulate it as a bilinear optimization problem. If you've never seen this, this is linear programming. Because all you do is take the dual of one of those and it becomes a min-min problem. Not only that, in the dual, yeah, this looks like mu multiplies v. You take the dual, they add. So it becomes linear programming. This is not hard to do. You use it in this context. The difficulty with this, number of pure strategies is exponential in the number of information sets. Number of information sets is exponential in the number of stages. Exponential of exponential is never happy in this idea. Okay, so you say, well, let's switch. But we have perfect recall. Long-term game theory tells us that if we have perfect recall, we can use what we call behavior strategies, things that depend or are just randomizations over actions in information sets, something different. And so the number goes down. You can now write interesting linear. The problem with behavior strategies is that the performance product is not linear in the behavior strategies. It's multiplicative in the behavior strategies. And you say, I don't like that. But there's a reparametrization due to von Stengel, Megiddo, and Daphne Kohler, and among others that pursued. This is called the sequence strategy form that converts that back to linear programs, bilinear solutions, which eventually result in min-max and max-min problems that are linear. Beautiful. The number of variables now is only exponential in one of the areas. This is easy, but hey, this is okay. This is less large. It means that you can hopefully attack some small problems with it. And people love this. Indeed, if you look at computational game theory, say, we go this way. By the way, we have done nothing to exploit structure here. That wonderful nested information hasn't been used. This is true for any extensive form of any Nash equilibrium game. Can be solved this way, as linear programs in this grand form using sequence parameterization. So can we do better because of the structure of the information that we've imposed? That says one player knows truth, the other one is on. And so we talk about, can we do some subgame decompositions? Can we do the equivalent of sequential decomposition that's associated with dynamic programming? And you look at sequential decomposition, and typical sequential decomposition requires, in the extensive game tree that you draw, a single node with all of its descendants contained in the subtree. That's the classic, Wilson sequential equilibria definition and things of that nature. You can do that kind of sequential decomposition. The fact is, we don't have that structure. The structure that we have in this problem is the following. If this were an information set of the uninformed player at a particular stage, the subtree, the subgame descending from that is all contained within that particular descendant. They don't cross from different information sets. They don't overlap in this context. That's because, this is the uncertainty that he has. The rest of the actions here are based on full information. There's no uncertainty by the other players. So, and because of the perfect recall, it contains the full subgame. That is sufficient to prove some interesting structure to come up with a decomposition layer by layer of the uninformed player's information. Now, notice, however, that there are multiple steps between subsequent layers. So this is like dynamic programming, but with games in between, not with optimizations in between, not with sequences of optimizations in between, and with games with incomplete information between the two players. That's fine. So what happens? We can prove two things. Number one, we can prove a characterization result. And this is purely a linear programming argument. The optimal value function depends, for any one of those subgames, it's basically a convex function, a maximum of linear functions of the probability distribution on the atoms of that original information set. This is fine. It's a characterization problem. Why is this useful? In stochastic control for finite state Markov decision processes, that same characterization appears. The optimal performance is a maximum of linear functions of the beliefs of the conditional probabilities. This is happening in a game structure, but and there's only one player with beliefs here. The other player knows everything, but it's basically your value functions are going to be linear functions of those, maximum of linear functions of those beliefs. And this just comes from the fact that it's a linear. The polytopes we're talking about have finite numbers. Linear programming, therefore, is basically a finite maximization in this context of this form. Now you go next. This is more of another qualitative result. If you had a saddle point set of behaviors for the full game, and you restrict it to the subgame, those would also be saddle points in the subgame. This is acceptable. It's not, you can almost believe that. Now what does the induction look like? Well, at the base level, it looks like that one stage game we solved. There's a two-player game where you start with incomplete information. You very quickly get a payoff that's piecewise linear, maximum of functions, acceptable. And you solve for that. You get a representation value of that. Now the question is inductively, can you now generate it to higher level values? And the fact is our algorithms are able to do so. You can show by induction a construction that allows you to take the support hyperplanes that are using for the value functions of the lower information set for the set of informations that descend from this one. So, from any one information set, there's a set of information sets that are descending that you got, because there are actions by the opponent. There's also actions by nature that result in potentially different sets here. Great. For each of these being maximum of linear, you can show that the solution of the game problem that results from that, with these payoff functions at these nodes, are going to also be maximum of linear. And you can come up with a representation of what those linear support functions look like at the higher level as a function of all the linear support functions of the lower level. It's a bit tricky. You have to conversify the space of support hyperplanes. You have to embed it into a larger min-max game where the choice of hyperplane that minimizes is also, quote, a pseudo decision. But at the end of the day, this is one of the key things we're able to establish, that we have that decomposition that's valid. So the main algorithm allows you to get the value function recursively. But it doesn't allow you to get the strategies recursively very easily. In control theory and dynamic programming, it's easy to get the value function, and then we get the control by substitution. Now you have value functions. The question is, what strategies achieve those values? That's a solution of another game. There's some linear programs to be solved on the way down to solve that. There's a nice forward algorithm that allows you to do that. But at the end of the day, you show that behavior strategy obtained by this obtains saddle points of the original game. And that's one of the key things that you were hoping to accomplish. So, is this fast? After all, you're solving for feedback strategies of all possible initial distributions as opposed to a linear program for the fixed linear distribution that you started with. Well, this is how it scales up for a fairly simple problem of this form. I mean, this illustrated how it would work. Frankly, it's probably not worth, given that we have dinner ahead of us, to go through this example. Let me tell you a couple things that I'll go to a better example later that may have something. So what's wrong with what I've given you? Well, remember, it's a tree. Trees grow. the number of information sets is growing exponentially with the number of stages that you do this. So therefore, if you had to learn support linear hyperplanes for each of the information sets, which we do, that's what we basically said, and then combine them recursively upwards, that's still a lot of computation. It's still growing exponentially with the number of stages in computation. And so we need more structure. In control theory, we gained that structure from Markovianity. And so indeed, if we were to put Markov structure, that the state evolves Markovian-like, only depending upon the actions at the stage, so it serves as a memory, then that tree narrows to a tunnel. All the information sets at the different stages kind of collapse into a single information set at that stage. And so we only have a single representation to learn per stage rather than learning multiple representations for each stage in this particular context. So Markovianity fundamentally is a major complexity reduction technique that we exploit. And you can show there's a formal definition of what Markovian structure means for us, which is for every two things that have the same history, with different history with the same state, if you take the same actions afterwards, they have to have the same consequences and the same payoffs. I mean, this is just kind of the obvious definitions that you deal with, but if that happens, then you can aggregate, you can show that you get a great reduction, which is that the solution of any game starting at time t can be represented as a single piecewise linear convex function maximizing over other pieces. And these are kind of the two theorems that are required to show that. Let me show you a little more of the example, just to highlight and compare. This is an example with a few nodes. We're allowing multiple stages on the examples we deal with. We're also allowing multiple attacks, things that you can try to attack and degrade these nodes. What you see here is a max flow problem with capacities and probability of success of an attack. It's 0.4, 0.5, some are higher and the like. And this is Cplex running on a fairly fast cluster, solving that linear program that was large but not huge. And this is our algorithm solving on a, what is this? It's an Apple. Thin Mac? No, what is it called? Whatever this Apple runs. This is running on this poor Apple Mac Air. Yeah, thank you. MacBook Air. And it's under a second. Whereas the Cplex version, when we allow 4 attacks and 3 stages to look at, didn't quite finish on the cluster. We just killed it after a day because it wasn't able to converge. So yeah, decomposition and structure pay off. Period. End of report. This is actually something that has been a theme in Demos' research all along. He's always tried to characterize the nature of optimal strategies first before doing computation and searching in this particular context. And indeed, that structure pays off. Let me finish this slide, and then I would love to get to you, if you don't mind, because this is my last slide, knowing that. So we have a new approach for solving this using the nested structure that I think pays off, although let me say the obvious, which is that, yeah, this is still works on toy problems. Let's agree that the 6 nodes, 7 nodes is not the largest network I would like to attack. But it might be one of the larger ones I can solve if I were to allow dynamics and uncertainty and things of that nature. Nevertheless, I can certainly do better than Cplex by a lot. So let's agree that it is an improvement. The theory has generalized nicely. We've got extensions in a couple of other directions, different orders of information, partial information in both players. You don't need perfect information, you just need nested information in this context. But there's some very hard extensions to be done in this context. So with that, let me conclude. Thank you. And Demos, congratulations, my friend.
Now, one special case of this is when X and W are independent random variables. This is a more sort of a traditional formulation. U0, U1